Hello, in this project we aim to perform a deep learning based classification and regression in order to classify fish species. The outline of this presentation includes problem statement, the data used for training and testing, research and methodology, results, challenges, and conclusion. Introduction to the problem. Seafood is the main source of protein for 3 billion people. Some species are focused for their limited numbers and prices. Most of fishing boats are equipped with high-resolution cameras which can provide good data sets for further analysis. This problem includes the classification problem, which detects fish species as shown in the top right corner in a fishing boat based on the image captured from various angles, and a regression problem for the localization of the fish on the boat, which finds the coordinate of the surrounding. Next part is about the data. The utilized dataset includes 8 classes, 6 classes for known fishes, 1 class for other type of fishes, and 1 class for images with no fish, and bounding boxes which contain values for x, y, weight, and height. The dataset includes 3 folders. 1 training folder with 8 subfolders for each class, test folder 1 and test folder 2. Name of the folder in which the image is located shows the class label. Annotations are provided in a JSON file for each class and consist of an image ID, a class, and bounding box information for each image. Research and methodology. Generally, there are 3 categories for similar tasks. First one is designing a CNN architecture from scratch, which is recommended when there are enough labeled datasets to train the model. Second one is the existing object detectors like YOLO, FastRCNN, SSD, RetinaNet, etc., which is mostly great for general object detection unless we could fine-tune it for our target goal. And the third one, which is our main approach, uses pre-trained CNN and fine-tuning for the goal application. State-of-the-art object detectors can be categorized as those with real-time detection like YOLO and YOLO v2, and those which are not real-time but have higher performance, such as SSD, FastRCNN, NASNet. Overview of the mean average precision score for state-of-the-art detectors on Pascal VOC datasets and COCO datasets is shown in the presented table. As it can be seen, a trade-off is made between high performance and the real-time prediction capability. We coded the project using the PyTorch framework. Standard CNN versus the faster RCNN is considered here. Accuracy and intersection over union metrics are used. IOU is calculated by dividing area of overlap into area of union. Regularization is accomplished by weight decay and data augmentation. The hyperparameters that are tested with different values to get the best set of them are pre-trained models, optimizer, learning rate, batch size, weight decay, data augmentation, and the loss function. Optimization of hyperparameters is done by using intuition. Because of the heavy computation costs, we didn't do the cross-validation. Pre-processing steps include resizing and normalizing the images and applying the same transformations to the bounding boxes. The first and main approach considered in this project is pre-trained CNN, which is the simpler one and uses ResNet34 and DenseNet121 pre-trained models. Last fully connected layer of these models is replaced with 12 outputs. 8 outputs related to 8 classes, and 4 related to bounding boxes coordinates. We use a 2-part loss function for classification and regression aspects of the problem. Cross entropy loss is considered for classification as and mean square error loss function for regression, which is weighted to draw more focus on it because of complexity of the regression part. As a second approach, one state-of-the-art model named pre-trained faster RCNN is employed. It is capable of managing many bounding boxes and requires heavier computations. We tested two pre-trained backbones in this part, which are ResNet 50 and MobileNet V2.
Okay, I'll be covering the second part of the presentation. For our data augmentation, we have two kinds, flips and filters that could be used simultaneously. For vertical, we have vertical flips and horizontal flips, also called mirroring. And then filters, we have both blurring and sharpening. For the results, we created this little table with all the tests that we attempt. Trying to classify a fish was basically having an image with a bounding box, and within the bounding box we'll have a fish, and then we'll just have to classify the type of fish that it was inside. Some of the results that we got were that the accuracy of the classification was very high, that we could not say the same for the IOU that reached at a base case scenario at 31%. The Atom Optimizer was the best, gave better results, and the learning rate of 0.0005 was a very good point. Any value lower or higher would just not give good results. The deeper networks, ResNet 101 and ResNet 34, had some issues with overfitting. This could be improved with data augmentation. We also had some issues with data illumination when pictures were taken at night. And also, we had to deal with data augmentation and weight decay, that we noticed that they were not working consistently in all the models. Some models improved with these features, and other ones did not have any changes. Here, we're just trying to show confusion matrix, that we see that the item number 4 is images with no fish. And in most cases, images were being misclassified as having no fish when there were fish, as we can be seen here. We had two approaches. One was the faster RCNN, and that did not give very good results for both the accuracy and the IOU. It was very hard to find the right hyperparameters because it will take a long time just to train this model. There could be better ways to improve this model, but we were not able to find them. Then we used the standard CNN that gave very good results for the accuracy. The IOU was satisfactory, but it was not as good as we expected. The only issue with this model is they can only detect one class per image. Some of the challenges we had was just trying to find the right results, the right approach for the faster RCNN. We, as I explained before, we also have issues with the images being at night, having different lighting. We also had to consider the issue with data imbalance within the train phase, where some classes had more data for training than other ones. And also just picking the right amount of hyperparameters. We had about 6 hyperparameters that were hard to classify and to find the right one, the right value for each one of them. So we can conclude that the CNN, the standard CNN, worked much better than the faster RCNN. The learning rate was the most sensitive hyperparameter, and we could also improve our project by just using different computational resources, just exploring more hyperparameters, just finding a better way to find them, and also just trying to deal with data augmentation, creating more features, and with that we could just deal with the data imbalance that we have in some classes. And finally, if we want to implement this project in the real life scenario, it could be used for authorities that are trying to just see the amount of fish species that each fishing boat gets. One could implement a camera that could just detect every time there is a new image, just take pictures when a new image gets inside the camera range. And then those images could be used to find the bounding boxes, and the just trying to see what type of fish is inside each one of these bound boxes. Well, with that, we conclude our presentation. Thank you very much.